Hello, my name is Oleksandr Romanenko. I am a PhD student at Kryvyi Rih National University, and today I'll share our research on a critical yet often overlooked aspect of condition-based maintenance, data acquisition systems. During our literature review on condition-based maintenance, CBM, we found numerous papers on data processing algorithms, machine learning models, and decision-making frameworks. However, data acquisition is remarkably underrepresented in the literature. Most papers simply state something like data was collected from sensors and immediately jump to their analytical methods. Considering this research gap, we decided to conduct a comprehensive study of the data acquisition process and data acquisition systems. As you can see in Figure 1, condition-based maintenance consists of three fundamental processes: data acquisition, data processing, and maintenance decision-making. These form a sequential pipeline where each stage depends critically on the quality of the previous one. The purpose of current research was to provide comprehensive analysis of data acquisition systems and develop a formal representation of such systems. We set out with four main objectives. First, to investigate the overall CBM architecture. Second, to clearly define where data acquisition fits within this architecture. Third, to study the data acquisition process in detail. And finally, to develop a formal mathematical model. Our first major result was the systematic decomposition of data acquisition systems into three fundamental subsystems, shown in Figure 2. The measurement subsystem serves as the interface between the physical world and our digital systems. This is where sensors detect vibration, temperature, pressure, or whatever parameters we're monitoring. The conditioning subsystem takes these raw sensor signals and prepares them for digital processing. This involves amplification, filtering, and analog-to-digital conversion, essentially making the signals clean and usable. Finally, the transferring subsystem handles communication, ensuring data reaches its destination reliably, whether that's a local server or a cloud-based analytics platform. What's important here is that each subsystem has distinct requirements and potential failure modes. By decomposing the system this way, we can optimize each component independently while ensuring they work together seamlessly. Now let's look at the mathematical formalization, starting with the measurement subsystem. We model measurement as an operator M that maps from the space of physical phenomena to the space of sensor signals S. In equation 2, you can see that the measured signal at time t equals the measurement operator applied to the physical phenomenon plus noise. The conditioning subsystem, shown in equation 3, is modeled as a composition of operators. Each operator C represents a specific conditioning step, like filtering, amplification, or linearization. The transferring subsystem, formalized in equation 5, captures the complete communication pipeline from source to destination. Equation 6 shows a composite model that represents data acquisition system as the composition of all three subsystems. In this paper, we've tried to demonstrate that data acquisition is a foundational process in condition-based maintenance systems, and many other systems as well, actually. Throughout our research, we've demonstrated that understanding data acquisition is critical for successful implementation of CBM. Our three-subsystem decomposition, measurement, conditioning, and transferring, provides a clear framework for understanding how physical phenomena are transformed into usable maintenance data. The formalization we've done provides a mathematical foundation for analyzing and optimizing data acquisition systems. In closing, I want to emphasize that condition-based maintenance is only as good as the data it relies on. By understanding and optimizing data acquisition systems, we can ensure that all of the subsequent processes have the high-quality data they need to keep assets safe and efficient. While this work provides foundational knowledge about data acquisition systems, we acknowledge several important research directions. In the context of maintenance, we consider further research focusing on optimal sensor placement strategies, adaptive sampling rate determination, and multi-sensor data fusion techniques that can enhance fault detection reliability and reduce false alarms. Thank you for your attention.